In this lecture 9, we are going to study how the PM junction is formed and how it is used for photo devices. So first, let's review the Fermi energy for semiconductors. Okay. In theory, the time equals zero. T temperature is zero case. You could see a flat valence band and conduction band distribution like this. So based on the definition of Fermi energy, the Fermi energy is the energy for the maximum energy where the electrons are occupied. So at temperature is zero case, since this energy, so this EF energy is 100% electrons are occupied, and if the energy is a little bit higher, there's no electrons. So this is the energy of the maximum energy for electrons. However, actually, this is not the real case, and in any cases, we have some temperature, and we studied the distribution of electrons is dominated by the Fermi-Dirac distribution. So Fermi-Dirac distribution describe the percentage of the electron occupying each of the energy state. For example, so at lower energy here, this one, at this energy level, electrons are always occupied in this energy level. And if it's go up there, there's no percentage, no probability of electrons staying in this energy level. However, in this region, there's some finite probability that the electron stays or not. So how can we define the Fermi energy in this case? And then the definition of Fermi energy is changed, like when the probability of the electron is 50%. So 50-50, you could find the electrons at this energy level, and 50% you cannot find any electrons in this state. So this is the definition of the Fermi energy for the actual the finite temperature case. Okay. So I'll move on to the N and P type semiconductor case. So here's the N type semiconductor. So I would like to remind you that N type semiconductor has a donor which has some extra electrons, like phosphor, and then it gives extra electron. So additional electrons. So additional electron can be easily excited to the conduction band, and due to the mobility of these electrons, these electrons are the majority carrier to give the more the conductivity for semiconductor. Okay. On the other hand, in the case of P-type semiconductor, you have acceptor level, which is, for example, boron or some other atoms which which can have mostly the less electrons than the silicon, for example, and this acceptor can accept the electron from the valence band that gives a positive charge in the valence band, which gives the conductivity in the P-type semiconductor. That's why this kind of doping is a key technology to control the conductivity of semiconductors. Okay, so what we are studying right now is Fermi energy. So as you see, here's the donor level, right? Donor level, and electrons are excited. So based on the definition that Fermi energy is defined as an energy level with half 50% the energy level is occupied by electrons. And since there are many electrons somewhere in between the donor level and the conduction band edge, so there should be some of the distribution ratio percentage like this. So in the case of N-type semiconductor, the Fermi level is actually in between the donor level and the edge of the conduction band. On the other hand, in the case of P-type semiconductor, based on the similar consideration, the electrons sometimes you can find in this acceptor level, and sometimes the electron is lost in the valence band. So the distribution where you can find the electrons or not is somewhere around like this. So what we can find is the Fermi energy is in between the donor level and the valence band edge. So somewhere around here. So this is a definition of the Fermi energy for semiconductor case. And I would like to emphasize that Fermi energy is kind of the energy where electrons can be exchanged from outside materials. Okay. So if you have a Fermi energy somewhere around here, and if you have a contact with some material which has energy, the Fermi energy is higher, this semiconductor is going to accept electrons. But on the other hand, if some of the material energy level is lower than this Fermi energy, the electron is given from the semiconductor material to the outside materials. So you can use that Fermi energy is the criteria where you could exchange the electron. Okay. So now let's think about the junction. So because in any photo devices, we are going to use the combination of materials, and if you combine the two materials, these materials are going to exchange electrons, and then at some equilibrium, these two Fermi energies must be equal. So what it means here? So Fermi energy is like chemical potential for electrons. So let me remind you that the chemical potential is gives energy per 1 molar for chemicals. So if the and for example, in a solid and liquid phase change, you need to have the same gives energy, meaning the chemical potential for equilibrium to have a liquid and a solid state, or liquid and gas state. And for each chemicals, the chemical potential must be equal throughout the space. Similarly, the Fermi energy is like the same meaning of the chemical potential for electrons, meaning that if you have a two different Fermi energy and if you have a contact between them, they must be equal. So how to make this Fermi energy equal? For example, if you have a higher Fermi energy material and lower Fermi energy materials, meaning that for these materials, the electrons are somehow higher energy, right? So it means these electrons are moving toward the low Fermi energy material. And then, since these electrons are lost, this Fermi energy is lowered. On the other hand, for this material, since electron is coming for the lower energy is occupied and electrons are coming, so this Fermi energy is going up. So what happens here is the higher Fermi energy material lower the Fermi energy, and then lower Fermi energy material move the Fermi energy higher. And then until the balance of Fermi energy is accomplished, electrons are transferred. So what happens at the interface is you will see that the positive charge, so since electron is lost, the positive charge accumulated at the surface. And on the other hand, this side that you have more electrons on the surface. And then these charges are balanced to give the charge balance. Okay. So let's move on to the contact between the semiconductors. So let's think about the P type and an N type semiconductor contact. Okay. So what we can think about here is you have N type semiconductor, meaning more electrons. In P type semiconductor, the less electrons, right? Because the Fermi energy is lower. So based on the contact between metals, you can think like the electrons from the N type transfer to P type, and then these Fermi energy can be balanced, right? So what happens here, based on the metal contact, you can imagine like the donor levels, the Fermi energy is lower and the Fermi energies become higher until the Fermi energy for N type and P type balanced. And since the electrons are transferred to the P type, and then in the N type, electron is lost. That's why at the interface, you could see these positive and negative charges at the interface. But this is actually not true and realistic the case. It's not a realistic case. In actual, the thing different from the metals and the semiconductors. you have to think that there are not so many electrons. There are not so many electrons and holes. Electrons are the acceptors, meaning that you cannot have much electrons to compensate the Fermi energy shift for N-type and the P-type. So please think about for a while until you can draw the energy level for P-type and N-type contact by stopping the video. And then I'll draw this here. Okay. Then, so what happens here is something like this. So what happens here is band shifted for N-type and P-type, but the difference you can notice is this region, right? So then, since there's not so many electrons, you cannot shift the Fermi energy in a very short scale like metals. And actually, this width has somewhere around 1 micron order, so which is quite large for thinking about the semiconductors is fabricated on the scale of nanometer these days. And how could it happen? Here. So on the N-type semiconductor case, so since you have extra electrons in the donor state, and originally it is excited towards the conduction band. And on the other hand, here in the P-type, it's going to accept the electron and making a hole if this is open. However, if you have a contact between these N-type and the P-type semiconductors, the electrons is actually, this electron is captured by the acceptor level, right? Because this one wants electron, and this one want to give the electron. That's why if you have a contact between the N-type and P-type, the donor level electron is accepted by the acceptor level. That makes since the electron is lost, the N-type side is become positive, and on the P-type side is negative. But this compensation is limited by the donor and acceptor number. Acceptor number, right? That's why gradually compensated. That's why this band bending for gradually Fermi level is gradually shifted to give the compensation. That's why you have some width of this region for transit compensation. And this region is called depletion depletion layer. Because in this region, since electron is given to the P side, and then the donor level and acceptor levels are kind of not working for generating the electrons charge carriers. So in this region, no charge carriers. Okay. So here's a kind of summarized sentence. In the donor side, since the electron is removed towards the acceptor side, so the electron cannot go to the conduction band to generate the conductivity. On the other side, and acceptor side, this originally accept the electron from the valence band, but this side is now occupied by the electron coming from the donor state. So no holes are generated. This is the PN, called the PN. This junction is called the PN junction.